we're very happy to have this opportunity to present some of our works here. For the people who don't know SLF, it's kind of a very old traditional research institute in Switzerland. SLF stands for Snow and Avalanche Research. This institute exists since more than 80 years in Davos in Switzerland. And nowadays we are part of the ETH domain, which is the university ETH Zurich, which is one of the top 10 universities in the world. And then we are belonging to the Swiss Federal Institute for Forest, Snow and Landscape Research. And the part dealing with snow and natural hazards is the SLF in Davos. And recently we started a new group called Alpine Remote Sensing. It just started 1st of July, so it's pretty fresh. And we're happy that we can present here some of our recent work we did. Elisabeth, she's a PhD student working for us since more than a year now. And she did, as she will present you, a lot of work with satellite images, interpreting satellite images and getting out the locations of avalanches in these satellite images. So please, Elisabeth, I hand you the word for the talk.
Thank you, Yves. Welcome also from my side. It's really nice to be sharing some of what we've been doing. And so the structure for today will be that I'll be sharing on large-scale avalanche mapping with satellites for about 2/3 of today's time. And then Yves will be giving you an insight into photogrammetric snow depth mapping. And with that, we'll dive right into the satellite mapping from satellites. And I want to start off by giving you a bit of a background. You all probably know the Swiss Alps, and they are famous for skiing. That's what you probably know them for. And in that context, avalanches are a topic. And but to be honest, like the whole population and the country has dealt with snow avalanches for a lot longer. That's been part of everyday life in winter in the mountains. And the way that Switzerland, but also the neighboring country Austria, is managing or has managed avalanche risk has actually been acknowledged in tangible cultural heritage. So you can see that it's a big thing. And part of that is also, of course, our institute, which Yves already mentioned, was founded in 1943. And for managing avalanche risk and risk management in general, it's really critical to know where avalanches occurred in the past and how far they went and where they came from. And that might sound like easy information because, I mean, you can observe it. But the problem is that you can observe it close to infrastructure that's accessible in winter. And then there's a lot of area that's not accessible where you don't have information. So the whole data is really, it's actually spatially biased. In some places you have a lot of information and others you don't have any information at all. And that makes it difficult for the risk management and for just like dealing with that whole thing. And the nice thing about satellites is that they're not restricted by avalanche danger, not restricted by accessibility, which is the reason why research using them to map avalanches started more than 10 years ago, not only at SLF, but also at SLF. And what we're going to focus on now is the large-scale avalanche mapping with satellites. And what I mean by large scale is 10,000 square kilometers up. And how this started for us at SLF, it started with a large snowfall event in the beginning of January 2018, where we had up to 2 meters of fresh snow in parts of Switzerland. And that resulted in the highest avalanche danger, which is danger 5. which you can see right here. You can see where it was forecasted. That's actually the avalanche build then for that period we're looking at. And that was actually the first time danger scale 5 was forecasted again after the avalanche winter 1999. And we were asking ourselves whether or not we would be able to capture the avalanche activity that we were in parts already hearing about, but also that we were mainly expecting because of the forecast, whether or not we could capture that with satellite data. And in order to find out what kind of data would be suitable for that, we decided to order a variety of data in rapid mapping mode. Rapid mapping mode means that images are acquired really fast. And here you can see a map with the extent of the images and also like the types of images or data that we acquired or we asked to acquire. And what we did is analyze this data and kind of like find out and figure out what would work best for a large scale avalanche mapping. And we came to the following conclusions. For radar data, we found that even though it's all weather capable, which is awesome and definitely an advantage over the optical, it takes quite a bit to go from raw data to processed data. And then even the processed data is a lot harder to interpret than what we know from the optical. It's challenging, and we did not really have those resources at our institute. And then for the optical very high resolution satellites, so I'm talking about Pleiad and Worldview, the problem with them is their resolution, spatial resolution is awesome. You can see a ton, but the problem is they can only acquire images from limited areas. And usually when you have an avalanche period, it spans over a wide range, like it's covering a larger area. And then you don't know beforehand where the hotspots are, where the most interesting or most destructive avalanches that you want to capture have occurred. And so it's really a disadvantage because you will never get the location right, or hardly ever probably. And then what we found was that spot 6 and 7, which is the satellite constellation, that they have the best trade-off between the spatial resolution of 1.5 meters and the ability to cover a very large area. So for example, all of the Swiss Alps. And we also found that in the RGB and near infrared, there's good information in there. You can work with this kind of data, which is why we concluded that that's the satellite to go to when you need those kind of images in the future. And another thing we learned was that we need to do proper georeferencing, and the quick and dirty that the satellite providers do is fast, but not good enough for what we need. And we didn't know that at the time, but actually the period to take advantage of that knowledge and to kind of like put what we found out into action followed quickly. We had another period with very high avalanche danger around the 22nd of January 2018. You can see the extent here in the black checkered. And then there was another period in 2019, which you can see here on the bottom. And for both of those periods, we activated the rapid mapping chain, which is like a way of acquiring data and working together with the Swiss authorities so that works quickly. So we ordered spot data, and then what followed was a manual interpretation and a mapping of all the visible avalanches. And that was done for a total area of over 20,000 square kilometers for both years. In the maps to the right, you can see a blue dotted line, which is actually giving you the extent of the imagery we acquired, which is called research area here. And in 2019, you can see that we acquired a lot of data outside of danger level 5, which was also interesting, kind of like for the comparison. And for the manual mapping, we also used additional data, not only the spot imagery, but also like a hill shade, aerial images from the summer, and a slope, for example. And to give you a better idea how an avalanche looks like in a spot satellite image, I've put you an example here. And you can see that this is example you can see a lot in the sun, right? You can see that has a blue hue where their satellite, where their avalanches mapped. You can see the forest. You can see some protection structures here. But here down in the shade, you can hardly see anything. And that's not that the data doesn't contain any information there, but for the human eye, you cannot like adapt the visualization in such a way that you can see something in both sun and shade or 16-bit data. So we actually had to like map in the sun and in the shade separately. So the shade would optimize for the shade would actually look like this. You can't see anything in the sun really, but you can see a whole lot more than before in the shade. And with this mapping and identifying avalanches in both sun and shadow, we mapped a total of over 24,000 avalanches for both avalanche periods. And we mapped them as polygons, as you can see here. And we also added attributes to them. So for example, the avalanche type, is it a slab avalanche or a glide snow avalanche, in order to like keep that information. And I put down here that it took approximately 2 minutes per avalanche for the mapping. And if that doesn't seem too much at first, right? But if you do the math with the number of avalanches, you end up with a couple weeks mapping time. And that would, of course, prevent any near real-time applications, because the data simply isn't available that fast. And so what we were wanting to do and wanting to move into is like automation. But like, for example, the thing you could think of would be machine learning, right? This is an awesome training data set you can use for machine learning. But before you would like build up a whole model on those avalanches, it would be good to first know how reliable they are, right? So that's what we did. First, we did that with a mini analysis, about 13 avalanches, which already showed that, yeah, that looks quite good. 73% of the area is correct. In illuminated areas, it's better than shaded areas. But I mean, 13 avalanches out of 24,000, it's not really a deal. That's kind of like a bit too little. We need to like have something more reliable, more comprehensive. And so that's what we did. We did a comprehensive evaluation around Davos. You're seeing Davos is located right here. And that's our study area of about 180 square kilometers. And we were looking at the 2 avalanche periods that I have already mentioned before. And we were relying on ground truth from photographs. Those were photographs, oblique photographs, taken either from the ground or from helicopters. And in order to like have a bit more information than just know how reliable spot is, we decided that if we actually take the effort to do such an evaluation, we might as well include other data that you can map avalanches from. So in addition to spot, we included avalanches mapped from Sentinel-1, which is a radar satellite with about 10 meters resolution, and Sentinel-2, which is an optical satellite with also about 10 meters resolution. And then we also compared a ground-based manual mapping method, or we evaluated it. And what I need to say and note is that all of those methods were mapped before evaluation and mapped by people who were unfamiliar with the other mappings and also with ground truth. And here I have, don't be scared, I'll explain. This is the 2018 avalanche period, and this is the 2019 avalanche period. On the top, you can see the evolution of the avalanche danger with the legend down here. So we can see that, for example, the 22nd of January 2018, we had very high avalanche danger in 2018. And then with the black dotted line, this is our validation period. So we're not considering avalanches before or after this period. And then you can also see the acquisition dates of our satellite images, and also when our ground truth was taken. And if we now move forward, I'm always talking about ground truth. How does that look like? Here you can see an example of an image taken from the helicopter. And those of you who are like, kind of know avalanches will probably spot at least one right away. And for those of you who are not so familiar, I have marked them with the red line here and here and here. So it's 3 in the foreground. There's some in the background we're not going to look at. And then in order to give you an idea about our validation procedure, we've put validation points in those places where we detected and where our ground truth showed an avalanche. And then we connected this. We connected this to the avalanches mapped from the satellite imagery. So here you can see that spot also has those 1, 2, 3 avalanches. That Sentinel-1 also has like some patches in those places, but also something to the side that's not really located where I think I remember the avalanche was. And then this was compared, like connected, not compared, connected, as we compared. And here we now have validation points. So in point 1, 2, and 3, the attribute would be, yes, there's an avalanche, it's true. And for point 3, if we look again, we can see, oh no, there's no avalanche here. So this one would be a false detection. And we dealt with all avalanches or with the whole area like this and ended up with 502 validation points, where 445 represented an avalanche, and in 57 locations we could prove that there wasn't an avalanche. And of course, when you've identified points like this and given them attributes, you can calculate statistical measures, so the thing that you're actually interested in. And what we looked at was the detection rate per size. So avalanche size according to the European Avalanche Warning Services. And then the probability of detection, where we wanted to know of the avalanches identified in ground truth, how many were correctly detected by a human in the satellite data. And then we also wanted to know the positive predictive value. If a human visually detected an avalanche and mapped it in the satellite data, how often was it really an avalanche and how often was it not? And here are the formulas for that. And with that, we're going to first look at the size distribution. You can see that one would expect that there's most size 1 avalanches and then it decreases to size 5. And as this distribution shows less size 1 avalanches than size 2 avalanches, we suspect that those were missed because of resolution of the photographs. And that's why we did the analysis of POD and PPV for size 2 to size 5. And if we now look at the detection rate per size, we can first look at, let's look at Spot and Sentinel-1. We can see that for both of those methods, avalanches of size 4 and 5 were very well detected, almost complete or complete. And then we can see like this decrease of size also for both of those methods. And we can also see that this decrease is a lot more pronounced for Sentinel-1. It's less than half of avalanches being still detected from Sentinel-1 imagery, whereas for Spot it's still over 90%. And this is probably due to the spatial resolution. And then what we can see here for Sentinel-2, we can see that there's no real pattern that connects detection rate and size. And the overall performance is weak for I mean, any size avalanche. So we concluded that Sentinel-2 has too coarse a resolution and it's not suitable for avalanche detection. And then here we have the manual mapping, and we can see a huge difference between 2 years. So it's actually dependent a lot on the person mapping. And if we now look at the probability of detection and the positive predictive value for all of those methods, I want to focus first on the overall POD, and we can see that Spot manages to detect 3/4 of all avalanches, and Sentinel-1 a bit over 1/4, missing especially the smaller ones like we saw before, and Sentinel-1, 2, not satisfactory. We're not going to look at this anymore. And then the Davos avalanche mapping, which we're also not going to look at. And then what we can see that the POD is very similar for Spot for both years. So it seems quite stable, not dependent on the avalanche period. And then for Sentinel-1, it's a huge variation that we can see here. And then the positive predictive value is good for all of those methods. I mean, almost 90% rightly of all avalanches were real avalanches is a good number, so that we can build up one. And now I want to focus on one aspect that's like specific for optical data, or in that case, I want to specifically look at Spot. And what you can see to the right is avalanches. This is actually where they start, and that's at the deposit. You can see some houses here, and there's a road here. And as you can see, they're going from partly illuminated terrain through shaded terrain and ending in illuminated terrain again. And we wanted to find out, as like over 30% of our study area were shaded. I mean, it's January. We wanted to know whether or not that affects the POD. And for that, we classified all avalanches using the ground truth. And we found a marked decrease in accuracy, or in POD, excuse me, for those avalanches that are fully located in the shade. So that's only 15% then. But for those that are in partly illuminated slopes, which would be those 2 avalanches here, as you can see, there's sun at the bottom, they're higher than the overall POD. So that's something that definitely needs to be kept in mind. And the peak for our study area of area being shaded would be at 43%. But then at the same time, if we look at the area that was shaded and the POD, we can see that it does not seem to be a linear relationship. There's other stuff playing in there, as 2019 doesn't have a lower POD than 2018. So there's some more research required in order to find out what really causes POD to drop, what also affects it, not only the shade. And then I want to focus on one specific and interesting aspect for the Sentinel-1 mapped avalanches. You might have noticed in the imagery that I've shown before that there are several patches that are not connected. And that's actually the case for 40, has been the case for 14% of all avalanches that we had in our study area. So it's something that the Sentinel-1 does, or the differences come out in best in different places and are not necessarily connected. And a lot of studies have pointed out or have claimed that Sentinel-1 only detects deposits. And we kind of looked at that, and we found that yes, the deposits are best detectable, but there's a whole lot of other parts that are also visible quite often. And what's kind of like difficult about Sentinel-1 is that the area of the patches does not correspond to avalanche size, or doesn't give you an indication of the size. And also, if you don't have additional data, you don't necessarily know what patches belong to each other, which is something that needs to be solved for, depending on what you want to use the data for. And so to sum up our validation results, the implications for the future are the following for SPOT. We would say that it has great potential for comprehensive mapping, but of selected events. Selected mainly because of two reasons. The first is that the data is costly. It needs to be ordered and acquired. And the other thing is that it might not work for all events, because we need cloud-free conditions afterwards in order to acquire meaningful images. And then for Sentinel-1, we can say that it's quite reliable for larger avalanches. With that, I mean size 3 up. And it would work well for frequent and even operational mapping. We have a passover here in Switzerland about every 6 days, which is, I mean, quite good. And I mean, of course, the great advantage over the optical, it's all weather capable. And then, of course, it's also free of charge, but that's not specific to it being radar. And so we did this evaluation, even though we only looked at 2 avalanche periods and we have a bit of a time lag. It's an almost comprehensive analysis, and we have evaluated all methods with the same methodology, which I find is really a big strength. And so we have the most complete validation to date. And what that kind of like opens the door for us to move towards automation. And that's what I'm working at the moment. And I want to give you a short outlook and share some of the things that I'm excited about and where we're like on the road at the moment. So I'm at the moment using a Deep Lab version 3+, so a fully convolutional neural network that has been adapted to better learn how avalanches look like. And I've been training that and evaluating the model with the manually mapped avalanches that we've been talking about ever since I started talking. And I'm using them for training, testing, and validation. And to the right, you can see a prediction that I've done with the trained model. And it's actually predicted on data that has not been involved in training at all. So you can see that it generalizes well. It's not bothered by it being another image that it hasn't seen, which is a good thing. And especially here in the illuminated parts, you can see that the avalanche outlines that are manually mapped in blue, they correspond really well to the area that it predicts. The darker the hue, the higher the probability, by the way. And what we can also see that here in the shade, it's having a bit more trouble. it seems to be harder to identify avalanches and learn how avalanches look like in the shade. So I'm actually working on this right now, and I'm excited to see where this goes, and I think it's really good results to start off with. And then for the future, we're planning on expanding this algorithm also to some other data that we have, like drone imagery and aerial imagery, but also, I mean, of course, satellite imagery is developing crazy, and we'll see what other data comes along that is similar to spot and maybe easier to get that we can include here and help to provide outlines for different applications in hopefully real-time or near real-time in the future. And with that, I'll be happy to take questions. You can raise your hand and then unmute and ask questions, or put them in the chat. We'll take about 5 minutes now, and if there's more questions, you need to keep them and remember them until after Yves' talk. Then we have more time for taking questions.
Can you hear me? I was told my microphone had stopped working.
Yes, I can hear you now.
Great. So if there's any questions for Elisabeth for now, if you want to drop that into the chat. As a starter, I was interested in whether there's any possibility to predict avalanches for the future. Maybe radar or something like that might enable prediction at some point in the future. Is that all possible?
Okay, I can start off, and Yves, do you want to, or Yves, do you want to take this question?
I'll let you answer first. Maybe I make an addition afterwards.
Okay.
So if we're talking about prediction, we're talking about snowpack properties. We're talking about properties of the layers that we have, and predicting the stability of those. And so it's an application that's actually quite far from what we're doing at the moment. There are efforts to map grain size with radar, but depending on the humidity of the snowpack, how far you can go into the snowpack is limited. And if you can't get to your weak layer, I think there are limits to predicting there. There is research, but it's not, I'm not aware of a lot going on, so bits and pieces. Maybe you can say some more here, Yves.
I mean, I acknowledge the visionary kind of the question of Tavi, but we would be happy if we could map the avalanches that have come down properly. That's what we're working on. Predicting is a very, very long way. Until now, I don't know of any remote sensing tool that has only a slight chance providing valuable information for predicting avalanches. But maybe in 10 years, I'm wrong. But for the moment, it's fact like that.
Roger, do you want to unmute and...
Yep. Thanks very much. Thanks, Elisabeth, for that contribution. Enjoyed that. Are any of the areas you're working on ever snow-free? And therefore, can you build into your machine learning what the base, the rock head, as I would call it, is like at all? Or are they all basically snow-covered all the time?
For the most part, the area that's snow-covered all year round is very limited. I mean, it's of course glaciers that we have in Switzerland and the high summits, but I mean the majority where we face or we have to deal with snow avalanches during the winter does not have snow cover in summer. For including the surface, I am including a height model at the moment, but I'm not using summer imagery, if that's what you were asking.
I was just wondering about anything you knew about the detailed terrain, the roughness, whether it was hard bedrock, whether it was likely to be loose sediments or anything like that. The kind of things people like Tavy are worrying about trying to find at the base of glaciers and ice sheets, that kind of variability.
To what I understand, that variability is not really relevant for the mapping of avalanches and for where they occur, because we have the weak layer in the snowpack, which is not, might be slightly affected by terrain, by warm air coming up and that causing faceting of the snow and the weak layer. But generally that's not a big issue, not something that I'm looking into as being a major contributor to the avalanches that I'm mapping.
Okay, thanks very much. Every day's a school day. Happy to learn that.
Andre, do you want to ask a question?
Oh, yes. Elisabeth, thank you. Very interesting. I wonder, you show how the detectability change between the different images, different type of images, but how this detectability change with time, maybe decay after the event. I understand, depends on the size of avalanches, depend on types of avalanches, but do you have some idea how the, what is the pattern of the detectability with time? Thank you.
Yeah, so from our study of finding out what kind of data is suitable, we had some pre-event images for part of our study area for 2018. And there we did like a mini analysis, in the sense that it's not covering the whole area that we were acquiring images at the end of January. And there we were looking at the avalanches and looked whether or not they were already visible in the images that we had from, I don't have the exact dates, but it's about 10 days earlier, and I think might be even one that's a bit even earlier than that. Don't nail me down on the dates at the moment. I don't have them in my head, but we found that about 25% of the avalanches that we had on the imagery from the 24th was actually already visible in the images that we had from before. Already visible means that either it was the same avalanche or it was another avalanche on top of one that we already had in the same avalanche track. So that does play a role, that avalanches remain visible longer. We don't know, like for that area that we looked at, we had the special case that we had 2 periods with very high avalanche danger. And so depending on the sequence of avalanche danger, you might have more or less older avalanches that are still visible. And that's the only thing I can tell you. We don't have the data to do a more comprehensive analysis and see how long avalanches remain visible, whether or not they become visible again when we have melting season in spring. That's all questions that'd be really awesome and nice to look at and answer.
Thank you. Thank you.
Okay. I would say we go now to the second part of the talk, and then we take more questions at the end. Otherwise, we run out of time a little bit. So I'm going to share my screen. Hope you can see it. We're not only mapping avalanches, but we also want to map snow distribution, snow depth distribution, because this is very, very variable in alpine terrain and clearly plays a big role also for avalanche formation. For example, wind-blown snow in avalanche release zones and all these things. And since several years, we're mapping avalanches, we are mapping snow depth by optical photogrammetry. And why is that so important for us? It's clear that the snow depth, and with the snow depth distribution, also the water stored in snow within the terrain. The so-called snow water equivalent is a key parameter for different applications, for example, snow avalanches, but also flood forecasting, drinking water supply, hydropower generation. Then very important in Davos is ski tourism. Is there enough snow for skiing in December, for example? It's a very big question. But also then what we research also at SLF is the alpine ecology, which plants grow where. And this is very often in the Alps connected to how long the snow cover is persistent in a certain area. So it's a very, very important parameter. The challenges on the other side are clearly that the terrain we are in is very poorly accessible. It's steep and dangerous. Often we cannot go there due to avalanche danger, for example. And then there is a very high temporal and spatial variability. I will show that in a later slide, what that means. And modeling is always nice, but you have to meaningfully validate these products, these model and measurement products. How do you validate that in such complex terrain? That's a key challenge for us. And today there are a few products around for the snow-covered area. This is pretty simple. I mean, there is troubles with clouds and so on, but you can pretty well map very snow and very snow with high temporal resolution and also high spatial resolution. But snow depth is a different story. Snow depth and snow water equivalent, there is not a lot of reliable products available. I would dare to say there is no reliable snow depth product available on a large scale with a high temporal resolution. So that's where we want to go. Spatially continuous, not just a point. Usually snow depth is measured at stations, but this is just a point, and a point is a point measurement, as you know, and not a spatial continuous measurement. It has to be accurate and reliable. So at least in the decimeter scale, it should be accurate. If you have high snowpacks like we have in the Alps, then it should cover large areas. The final aim would be a product that goes on the global scale. It has to have a high temporal resolution, should have information every day or at least before and after larger snowfall events. It should be economic. So today everything should actually be free and open access available for everyone. And it has to be meaningfully validated. So we have to be sure that this product is really accurate and reliable. So the first approach we tested since several years now are drones. These are not drones that we build ourselves, that are off-the-shelf drones, commercial drones we apply. And this was kind of a key map for us. It was the first map we did of an alpine snowpack very close to our offices in the ski resort, where we mapped snow depth distribution. This was in January. At the mountain peak. The peak has an elevation of around 2,400 meters. And what you see here is how extremely variable the whole thing is. And if you look at these strange lines here, these are the hiking path. So why do we see the hiking path in a snow depth map? We see it because they're a little bit concave, but the snow depth above it is smooth and homogeneous. So you see this small variation in snow depth in this map. And this was for us a really nice result because we saw that it's really accurate. And we see a lot of details in this complex snow depth distribution. This is also a nice picture to show people what snow depth means in alpine terrain. It's not just kind of a cover that has the same height all over, but it's used variations. Here you have variations of 4 meters, and within 1 or 2 meters, you get to some centimeters of snow. So the variation is very, very large within very short areas. And we validated a lot because we wanted to quantify how accurate our snow depth measurements with drones are. So we did avalanche probe measurements thousands of Avalanche probe measurements. Oops. And this is one of the results. This was also very good for us to see that we can map all the snow depths between 0 and here up to nearly 3 meters very accurately. We get a very good correlation between the photogrammetric snow depth and the reference snow depth. So we can prove that this is accurate measurements with drones. And we have a lot of applications for this. This is a picture of winter 2018, also close to Davos. You see these avalanche barriers here. They are here nearly filled and up here completely filled. And you see these wind fences here that should prevent the snow from being deposited within the defense structure. And if we map now, you see in that example, we mapped this area with drones, and we can very well visualize how these wind fences, you see one here, and you see one here, and you see some up here, how they work. So down here, they work very well. The main deposition of the snow, more than 5, 6, 7 meters, is deposited right after the wind fence and not within the avalanche barriers. On the other hand, here, where we have the zoom, the wind fence is way too close to the defense structures, and the effect is the opposite of what they should do. So all the snow is deposited directly in the avalanche defense structures, filling them up very quickly and making it very dangerous for large avalanches, endangering houses and roads down in the valley. So this is a very nice example of how we can apply drone-based snow depth maps for monitoring mitigation measures. And with this accuracy and reliability, this is very well possible. So the main advantages of the drones is that the data we get, snow depth maps, is really accurate. It's in the range of 10 centimeters. We can apply them very flexibly and frequently. If someone calls, we can load the battery, sit in the car and go and map these areas of requests. We can also do that if we have high clouds. I put that in brackets because then we have lower contrast and we get into some trouble with homogeneous snow surfaces to do photogrammetry, but it still works reasonably also under high clouds. And we have a huge technical development of drones, so there's better sensors, better equipment coming on the market nearly every week. So I think there is a lot of potential in that. But there is always disadvantages. For drones, it's clearly the limited coverage. So what we can fly now with a reasonable effort is something like 5 square kilometers with our fixed wing drones we have. That's quite a lot, but it's not catchment scale, that's clear. Then the legal regulations, we are pretty lucky in Switzerland that it's quite liberal, but you never know how the regulations change of flying drones. I think in other countries like the US, it's already nearly banned to fly drones. So that would prevent us from doing that work. And then if we have high wind speeds and a very bad illumination, cloud cover, a lot of shadow, it's getting difficult. And you clearly need to frequently fly the drones, to fly them in this terrain, to stay up to date and to have enough exercise to perform these flights in this complex alpine terrain. The second approach we use is manned airplanes. We started that in 2010 with this Leica ADS scanner. This is a push broom scanner. And now we switched since 2017 to the Ultracam Eagle survey camera system. And with that, we can cover a much larger area. You see that here. So the orthophoto is what we can cover in one flight. It's something like 300 square kilometers we can fly. And this is the Dischma Valley. This is our main test site. So the SLF Davos is right here where this station is. And here we have now more than 10 years of manned aircraft flights that we can compare. And we also have, as you see, a lot of automated weather stations in that area, which helps us to validate or at least estimate the accuracy of these data sets. And here you see an example of two maps in the Dischma Valley, in the back of the Dischma Valley. And you see again this huge variability. So this is on the left, we have 2020, April 2020, and on the right, we have April 2021. And you see that the patterns, the main patterns, they are pretty similar. But you see that we have quite a bit more snow same time of the year in 2021 than in 2020. But this is very, very interesting data sets for us for many different applications at SLF. It's very nice to have these data sets now for 10 years, always close to peak of winter. And with that, we could make for the entire area a comparison between the station measurements and the mean snow depth with the ultracam. That's the red box here. And you see, if you take the mean of all the stations, that's the blue triangle, you hit very well the mean snow depth every year. And it's in the last 5 years, we had a huge variability with a mean of around 1 meter up to a mean of about 2.20 meters and back to around 1 meter. But this is very interesting to see. And we have one station here, the station Stillberg, which is hitting the mean of the entire catchment very well every time the last 5 years. So these are very interesting investigations. We're going to further elaborate with these data sets. So the advantages of the manned airplanes is clearly the larger coverage. We can cover more than 300 square kilometers, so really catchment scale. That is nice. The results are still accurate. It's the root mean square error is in the range from 10 to 20 centimeters. We have a fast data acquisition. Flying such an area is about 1 hour flight time. We need only a few ground control points in nicely accessible regions. And we could also perform that under high clouds. But again, with photogrammetry, we might run into trouble due to lacking contrast of the snow cover. The disadvantages are clearly the costs. So one flight we pay per year is around $20,000 US. So we're lucky that we can fund that for the next years, but it's a lot of money. Then you have to organize the airplane and the flight permissions, which is not always very easy. The Davos area is often the airspace is closed for WEF, for example, or also for army exercises. And then we get a large amount of data. So one flight, only the raw imagery is 1.8 terabytes. And then computing the point clouds multiplies the amount of data storage you need. So that's there you need really high-end computers or servers to process this data. The third approach we tested is satellites. It would be really cool to have snow depth from satellites. We used the Pleiad satellites, which can record triplets like we see here with 50 centimeter spatial resolutions. It also has RGB and near bands. And this is the result of the first test we did for the entire Dischma Valley satellite-based snow depth. Here we didn't any masking, so what you see here is the forests in blue, very high. And then here in the back, you see the small glaciers. They get very negative snow depth values because the glaciers lose a lot of ice year by year. We can also measure that with these data sets, but we are more interested in the snow depth distribution. So the advantages of the satellites is clearly the very large coverage. So you could cover several hundreds of square kilometers. They are already up there flying. There's more and more satellites to come. So there is a potential for getting more data. The data is acquired within some seconds. So a triplet is acquired within 30 seconds or something like that. Then you have acquired the data. You need no people directly in the field. You need to put some ground control points, but you can do that outside of our office. And then in the end, that would be the final aim, to have satellite-based SNOWDAP products. That would be really cool, and I think what we should really aim for. But we still fight with quite heavy disadvantages. The biggest one is the lower accuracy. So the root mean square error we get after masking everything and adapting summer and winter DSM is around 50 centimeters. And for most applications, 50 centimeters is not sufficient in accuracy. Then there is still, for these type of very high resolution optical data, there's high costs, a little bit less than the airplane, but still very significant costs, especially when you're tasking the satellites. And if you have clouds, also high clouds, the optical satellites are not working. So the conclusions are that photogrammetric SNOWDAP mapping works actually much better than we expected. So we could prove with different studies and investigations that we get very good accuracies and that we can map really most of the terrain. So that's good news. We can apply different platforms, drones, airplanes, and satellites. The main differences between the platforms are then the coverage, so small coverages for drones, large coverages for airplanes and satellites, and accuracy. But the accuracy is very strongly connected to the ground sampling distance, the resolution of the input imagery, and we won't get a very good accuracy if we have 50 centimeters GSD satellite imagery. Then the achieved accuracies depend on the ground sampling distance. That's what I just said before. And regions in shadow and with very homogeneous snow cover, they are hard to map. And sometimes we just generate holes that the algorithms don't find matching points. But surprisingly, this is usually much less than 1% of the covered area. So in most cases, we only have a very small part that we cannot map the SNOWDAP. This is also good news for us. So these are some recent publications, and with this is then the last slide for promoting the next talk. But now I would be happy to take some questions.
There were some questions already on the chat from the end of Elisabeth's talk. There was one from Hester, I think. You want to unmute yourself, Hester? And
you mean the one? Oh, I'll read it very quick. Would expanding this to non-optical imagery work as different approach that works under cloudy conditions? For example, surface roughness from SAR or other radar-based imagery. So what we did for the evaluation and what I also showed is that there are other groups that are mainly focusing on the radar part. So we have kind of made, like, through the circumstances of having two large data sets and kind of like ending up concluding that this is what works best for us, we have focused on the optical, but there's other groups that have been focusing more on the radar part. And I've also included, like I showed in the evaluation, one radar mapping in there. So there's other challenges for radar. Of course, it would improve reliability in terms of being independent from weather. And so that's happening. But there's other things like layover and radar shadow that you then need to deal with. Yeah, so I don't think that surface roughness from SAR, including that with optical, I don't know if you meant that. I don't know, I don't think that would improve. I hope I understood what you meant, and if not, need to ask again. Okay, yeah, that's good. And then there's another one that came in via Facebook. I wonder if the size distribution of avalanches is similar to that of earthquakes. There are only a few very large earthquakes and many, many very small earthquakes. Has anyone looked into Gutenberg-Richter style statistics for avalanche magnitude versus frequency or number? I have not, and I'm not aware of anyone who has. Someone has posted a paper in the chat that I don't know, and I will look into it, but other than that, I don't know. I haven't looked into it, and I don't know how the relationship is with this measure.
Are there any further questions for either of the two speakers today? Andre, do you want to unmute yourself?
Oh yes, I just wonder if it's possible to use ISAT data as just some additional source of information on snow depth.
ISA2 is an altimeter, is that right?
Yes, yes, yes.
Yes. Yeah, for sure, if it would be possible. I don't know exactly about the problems we're going to have with complex terrain. What is the footprint of ISA2?
Oh, I don't know exactly, just maybe first meters.
Okay, so it could be an option, but it will provide us, I don't know how many measurements within our research area.
Oh, well, I just wonder, maybe it's interesting to check.
I mean, I think it's a very good idea, but we are a bit, we are a bit lazy because we have so many stations already in the area there, and we are researching that area so intensively that we don't look too much into other options. But it's clear for other areas where you don't have this infrastructure, this might be the only other valuable source of data.
Just to control something.
Yeah.
It is free.
Yeah, we will have a look. Maybe this is also interesting. Do you know about the accuracy in Z?
Oh,
in XY?
It depends on the, rather accurate. It's a photon data. It's not just analog or data. It's, I just try to use it for ice crevasses and glaciers, visible and everything.
Mm. Yeah, thank you. Maybe we have a look into that. That's a good hint. Thank you.
Thank you.
Are there any last questions for the speakers? Okay, well, if not, I think we just need to say a big thank you to Yves and Elisabeth for their duet today, a really, really interesting set of talks, and to encourage everyone to come next week with a glass of French wine. It's Bastille Day, so that would be entirely appropriate to listen to John Bamber, who's going to talk about epistemic uncertainties in ice sheet projections. So hope to see you all next week. And if anyone is wondering, the football is still on. 1-1 and in extra time. So you can still see the finale of the football if you want. The seminar. So thank you very much indeed to both speakers. And thank you very much to the audience and all the questioners.